Hello. Today we are discussing a very important topic in business analytics, that is simulation, predominantly business simulation and simulation modeling, running experiments with simulation and reading the simulation output. So without wasting much time, let me start with my presentation, and during the next half an hour we will understand the definition of simulation, the process, and also take you through some hands-on examples of simulation. So let me start my presentation. And specifically we are dealing in business simulation from the point of view of operation and supply chain analytics. So we will be first talking about the introduction to business simulation, then try to understand what is the basic simulation terminology. Then we will come to simulation methodology, and then we will see some examples to see simulation methodology in action. Post that, we will be exploring big data with simulation. So let's start. So in introduction, simulation. So it's the most preferred technique while we investigate the behavior of complex business models, because not always possible to work on real business systems. So we have to work with a statistical model. So simulations offer an approach for descriptive modeling, and rather than working on the real business system or real business, we work on a simulated model. Simulations let you experiment with your different decisions and see the outcomes. So you can run your experiments, and it helps to assist management in evaluating different operation alternatives before you decide to go with alternative 1 or alternative 2. So operation wise, what is the most efficient or optimized or alternative you can choose while you run the simulations. In case by case basis, the simulation methodology can generate acceptable policies that are near optimal. So it also helps to see what policies gives you the near optimal solution, and you can take the appropriate decisions. And a lot of what if questions, scenarios about real world system, you can investigate them using simulation and then go with the implementation of the real system, because otherwise if you go without testing and simulating it and seeing the results, then reverting back on the real system implementation may be a very costly proposition. Simulations are also used to test new facility locations, new designs of the product, new production scheduling policies, or new transport scheduling policies without any costly disruption to the ongoing real system. The basic terminology of simulation, the first thing is the system. It's a collection of entities and sub-entities that interact with each other as they process input out to output. Simulation model is also a system because it represents a real life system. but rather it's a statistical system. The state of a system is a set of variables necessary to describe the system and their values at a given point. So you have normally in a simulation you have a dependent variable and which is influenced or caused by independent variables, and then of course there are some control variables which has to be kept constant. We also have to look at discrete versus continuous model. Sometimes these independent and dependent variable, when the state of variable changes at discrete point in time, we call them discrete simulation models. Whereas if the variables dependent or independent, they changes continuously, then we have to call these simulation model as continuous simulation model. And changes in continuous model are tracked over time according to set of equation, typically involving differential equations. Static simulation models represent the system at a given point in a time. Static simulation models are also sometimes referred as Monte Carlo simulation model. Dynamic models, however, represent the system over at a period of a time. Deterministic versus stochastic simulation model. So in a deterministic simulation model, you don't have any random variable, whereas in stochastic simulation model, at least one input variable is random in nature. Thus, the outputs are also random in nature for as far as the stochastic simulation models are concerned. So let's look at simulation methodology step by step. So the first thing is you have a problem. So you create a conceptual model. What is the goal of your simulation model? What is the output or what is the objective of the simulation model that you are looking at? Once you are clear about the objective, you are looking at input and output variables. What is the relationship between input variable and the output variable? You come up with a high-level process flow diagram. Based on this conceptual model, now you will have some hint about what are the information or data that is required. So, of course, based on your understanding to investigate or to simulate the model, to run experiment with it, what is the information required, and so you go ahead and go on with the data collection. So first thing, you can collect data through observation, get some transaction records that are available within the organization, or you can go for a field survey or collect the data from different systems or data records or transaction log files, and then you look at statistical fitting. What is the nature of your data? That is also very important to understand whether your data follows a input data follows, or the statistical data that you have follows normal distribution, or does it follows linear distribution? Does it follows sort of a Poisson distribution? So all this thing has to be considered. Then once your data is there, you do the statistical programming, or you statistically run the pilot run of the statistical simulation model. Of course, you have to make sure that whatever simulation model you are running statistically it represent, you validate it vis-a-vis how good it is vis-a-vis the real system that has been running on the ground, or that, so you validate it how good is the output vis-a-vis the real system. Then you make sure that for subsequent data sets you verify that the results are consistent as even for the different data set. That is called verification. So once your simulation model is ready, you have validated, you verified it, then now is the time to design the experiments. Basically the scenario analysis, what if scenario analysis, see any control variable that need to be kept constant, and then you generate hypothesis. Hypothesis means that if a particular variable changes, it whether it affects the output variable or it does not affect the output variable. So you generate the hypothesis statements, and we all know in statistics the null hypothesis, and that can be statistically proven wrong or correct. Then you run the number of applications. Subsequent, once your experiments are designed, you start running the simulation. That is a statistical running of the simulation model. Then you, after running on the training set, you run it on the test set, you look at the model behavior. Then you statistically analyze the output data, that output, the result that are generated from the simulation model. So t-test, you can do confidence interval analysis, t-test, you also do the risk analysis, and the reports are generated. And finally the 8th step, that is what is the summary of your output, the conclusion that you draw from these results, and any recommendation from the practical point of view in terms of decision making. Let's look at each one of them quickly. So first is, as I already explained, based on RFP documents, a business report or request from the management while you are interviewing them, you go ahead and start with the simulation modeling. Purpose of the study, based on these above sources, you can establish the objective function or what is the dependent variable that you are interested to explore. And the scope of study is normally defined by time required, the time you have in hand, and what is the nature of the organization unit which you are studying. In conceptual model, you start with identifying the goals of the model, what are the input variable, whether stochastic, that is, or deterministic. In terms of stochastic, means random variables, input variable is random or not. Then relations between variables are explored, how the understanding input variable affects the output variable. Intermediate variables are calculated if required. High level flow diagram is prepared or pseudocode. Final goal of the conceptual model, so we get a list of information requirements. What information is already available and something that is not available, what information need to be collected. In data collection, historical records, system documentation, personal behavior observations and interviews are conducted. Data should be tested. Input variable need to be independent in nature, they make sure that they are homogenized, and whether they are deterministic or stochastic. A computer simulation model is a logical model of the process must be developed based on data collected, and you model the construct of the simulation software. Basically, there are 4 elements: entities, location, process flow for entities, and process flow for resources. Several software packages provide the ability to generate random values. You pilot run with a limited number of applications, and in validation you compare the two results, and conceptual model is compared to the real system. If comparison true, then your model is valid. In verification, two or more results are compared for accuracies, and then once their results are consistent, then it shows that simulation model represents the real life system correctly. Not only it represents the real life system, but it also represents them correctly. Design experiments, basically, which is around if-then scenarios. Number of alternatives are tested and optimized. The best scenarios is chosen. In simulation runs, rather than just running one cycle, you can also get important insight by studying the change of the state of the system over time. In the analysis of the output, the statistical analysis of output variable is conducted. Points and interval are estimated to measure the performance of the system. Hypothesis testing and risk analysis are performed, and output reports are prepared. In results, final results, summary of the results, main findings, conclusions, and most importantly, practical recommendations are given to the management. The best scenario is identified, and best combination of decision variables is recommended. A little bit of caution here. Far-reaching decisions should not be solely based on the outcome of the simulation. They should be also based on the foresight and discussion among the top management to consider the industry and practical realities. Some of the examples we use simulation. Where we use simulation in business is manufacturing process. How well do sequences process interact with each other? In the warehouse, in the flow of goods, how do different picking rules perform? In routing, vehicle routing for a distribution system, which routing heuristics works best? For example, in service operation call center, how does the system operate with more staff or less staff? Inventory replenishment policies, how well do different reorder point and order quantity perform? So based on these are the different scenarios, I just given you some example, there may be many more, how simulation can be help among the differential operation policies, different alternatives, and based on the simulation one can choose the best alternative or with the best policy. Let me quickly run you through one simulation example so that we can see how does it work. Let me take you through one example. You have Mr. Subhash. He is running an inventory policy, basically inventory control policy, that he wants to have a reorder level of 15 units, and once the inventory reaches 15 units, he orders 30 units from the supplier. So order quantity is 30. Basically I can change it here. I can make it 30, make it 60. Suppose I have to say reorder level is 15 and every time just there. And the demand table, demand is, you can quickly see here, so demand is follows a probability distribution. So these are 3% for demand 0, 8% is demand 1, 3 to 8%, 8 to 13%, sorry, 8% to 21%, demand is 2, and between 21% and 46% demand is 3, 46% to 68 demand is 4 units, and this is per interval, and we are taking per interval in terms of days. Daily demand 68% to 88% demand is 5 units, and 88% to 1 demand is 6 units. So total cumulative, as you can see, the demand is 1. Similarly, the lead time also follows a probability distribution. 0 to 20% lead time from the supplier is 1 day. 20% to 70% lead time is 2 days, and 70% to 100% the lead time is 3 days. Total cumulative probability is in both the cases 1. So we create an output table here where the demand from the customer is shown by here, and what will be the demand, that is, so this is a stochastic distribution, stochastic simulation model where the demand from the customer is random in nature. And how do we do that? While we're doing the statistical, we have a function called equal to RAND and the close bracket. So if you see, if we come here and I can say all the numbers will change. So in the day 1 unit received beginning inventory, because you start with the beginning inventory of 30. The random number is 79, that's why it falls here. So you can see immediately the demand is for 5 units, which is picked up from the formula VLOOKUP E18, that is this number divided by table is B16, B6 to D12, and it will pick up the third. So this is the third one, pick up the number, corresponding number from here. So as you can see, 0.79 values lies between this, so it picks up the demand from the demand column that fits that number, so which is 5. So of course when demand is 5, the ending inventory becomes 25, the new level is 25. You of course, whatever this demand was 5, so you gave 5 from the inventory, lost sales is 0, of course there is no new order because you have a lot of inventory. Second day you start with the 25 because 5 units were supplied, random number generated 36, the corresponding from here to here, you can say 36 lies between here, the demand is 3 units, you supplied 3 units from 25 in inventory, you left with 22, new level is 22 units in the inventory. Did you lose sales? No, because you supplied the 3 units. Do you need to order? No, because reorder level is not reached. You continue till day 6. When you begin inventory 17, you have probability that is randomly generated is 36. So you have to have 3 units to be supplied. So once you supply 3 units from 17 units in starting inventory, you leave with 14. New level of inventory in hand is 14. Because you supplied 3 units, lost sales is 0. Now you have reached 14 unit, which is below the reorder level, and of course you need to place an order. Now here is, you look up at this random number. This random number, you can see, is, and then equally lead time is given as a 3 days, and the receipt. So from 6, if you place something on the 6th day, lead time is 3 days, you will get it on the 10th day. So as you can see, on the 10th day you get 30 units, and then on 9th day you had 4 units at hand. So once you get on 10th day, you get 30 units, and your starting inventory become 34. Render number is of course 42. Demand is 3. Again 3 units are supplied, 31. New level of inventory is 31, and you did not lose any sales. You have 31 units, which is far above the reorder level of 15 units. No new order is placed, and you continue. We run this simulation scenarios, and we continue to generate this table for 30 days, and we calculated after end of 30 days what is the demand during those 30 days, and did we lose any sales, how much sales was lost, which is 0. And service level, which is 1 minus lost sales divided by the unit orders, correct? So our service level is, as per the definition, and the calculation is 100%. So this is a good inventory policy to follow, and we are pretty much okay with that. But suppose this becomes 7 and this becomes 100, and you can see our service level has reduced to 93.4%. So this inventory policy may not be so good. Suppose our reorder level becomes 1 and our order quantity becomes 200, and again play with the random number here. Let's see. You can see our service level which is again, because 30 days and we have not, this is little bit too much to order. Let's say this is 50, just for the sake of illustration. Our service level has reduced to 87.5%, and while in a normal small business like this, which is such a small demand, we are looking at inventory policy of 100% service level, that whoever comes, we should have inventory to supply or meet the order from the customer. So probably this inventory policy is not good, and our initial inventory policy of reorder level of 15 and order quantity of 30 is a fairly good inventory policy for this store, and it gives us a 100% service level. So you can see, using a simple simulation, these exact formulas I can show you here just for the benefit. Fairly simple calculations where we are just looking at and we have shown you that how simulation is able to, using simulation modeling, you can check the inventory policy. Let me take you through one more example, which is a little bit more complex in nature. Here we are looking this. Okay, maybe I need to explain a little bit about this. This is second example of a blood bank agencies, and it is looking at collection from the people so that it can supply the blood to the hospital. And an agency which collect the blood from the people spend $150 to convert that blood into 1 unit of blood platelet that it can supply to the hospital. And from the hospital it gets $400 per platelet. And if demand from the hospital in terms of units of platelet is random in nature, so again it's a stochastic simulation model is required. And in case they have more inventory, they collect more blood platelets, unit of blood plates, and demand from the hospital is less, then this platelet cannot be stored forever. Within after 2 days it has to, or after number of days, weekly it has to be disposed of, and it takes $20 to dispose each unit of unused platelets. So agency should collect enough platelet to meet the demand from the hospital, but should not exceed the demand so that it doesn't has to dispose it of, because it costs $20 to dispose. So the collection policy to get so that its cost become the less and it doesn't dispose of also, and it just meet the demand from the hospitals. The platelet inventory management system is complicated because of unpredicted demand for a product shelf life of only few days. Now let's look at the stochastic pull system and the operational activities of the blood center for the last 1 year is studied, and weekly demand for platelets, which is an uncontrolled variable, is now put in a probabilistic distribution. So based on the last 1 year data, this is what is calculated. Weekly demand for platelet 300 units, probability is 10. Weekly demand for platelets 500 units, probability is 25%. 800 units, probability is 35%. 1000 units, probability is 30%. This is how, now let me take you through the Excel again just to show you. This is a simple calculation which I can show the formula to you. The collection level, suppose it is set as, so this is probability distribution 0 to 300, probability is 10%, 10% to 25% 500, 35% to 70%, it's 800, 70% to 100%, it's 1000 units weekly demand. Whatever we have last 1 year data, total you can see is sum of probability is 1. Now we are, suppose we are looking at collection level of 30. We want to generate a random number here. And it's okay. And based on this number, I enter and I look at this random number. Then I select this table and I select second. you can see this 45% is the number that lies between here, 35% and 70. So it picks up the appropriate number, which is 100. So this is randomly generated number from this is value is picked based on this random number, and the processing cost per unit is 150. We know that. Revenue per unit is 400. Disposal cost 20. These are the data that is given. So what is our total revenue? Is equal to revenue per unit into minimum of this and this. Fair enough? Because suppose we demand is 1000 and we collect 300, so of course we will be selling 300. Suppose demands become 200 and we collect 300, so we can only sell 200. So this is minimum. Processing cost, of course, is processing cost into how much is the value we calculate, and disposal cost is equal to if C4 greater than C2 is 0, because our demand is more than collection, so no disposal. Otherwise it is the extra collection so this is what is our net revenue is equal to this minus total minus cost minus disposal cost. Very easy. Now you can see our conceptual model, our model is ready. Now I have to run based on these different demand scenarios, collection levels. I'm running a scenario which is 1000 scenario. So you can see this table. And how do I get this value? I get this value from there's a very simple thing called data table. Correct? So I get this thing from simple calculation of I create a data table and I select my input, and depending on 400, 600, 800 unit, these are my net revenue. That is, so you can see here, this is, so I run approximately 1000 scenarios and I calculate my net profit in each one of these scenarios. So this is my data table, and you can easily create a data table for these 1000 scenarios with it. Now here, these are my output, 1000 scenario. Now I study the statistics of my results. So I do statistical analysis of these 1000 scenarios, and then I calculated average here, select this, and next value if I have to select. So I told you first value this, the last value is B1046. It will give you average of 1000, and then I can just drag it. Right, so each of the scenarios it gives me the average net profit or net revenue. Then I calculate standard deviation. Then again I select this first value. Then it's P106. Confidence. So it's for this alpha I'm taking as 5%, so 0.05, and then I choose K16. Standard deviation. This. In this case it's H16, and then I choose 1000, which is my sample size, and this would be 1000, so I can confidence to each of these 4 scenarios, and this upper limit is of course mean plus so you can see whatever is my 1000 scenario, I do a statistical analysis of these 1000 scenario, and it is given here. In case I collect 400, and then in that case collection level is 400, then in that case my mean is 96. So you can see different scenarios. I'm running 400. Suppose I run each of the thing. Suppose I set collection level as 400. I can select it as 400, 800. So within each of these scenario, what is mean of the net revenue is at 400 collection level policy is 95k, approximately 95.4k. For 500 is 1.17k, for 800 1.49. Then it goes down, which is around 1.41. Standard deviation, you can see the standard deviations are there. Confidence level, the upper limit, the lower limit, So one can, the statistics of the output also need to be analyzed before we can say which is the best. So if I do quick thing, then 800 level looks like the best level, the most acceptable policy to me. So analysis of output results and recommendations. So you can see 800, which is 149.5K dollars of net revenue, looks like the most preferred. But the output need to be analyzed, as I am reiterating again and again. That is an important step, because the common error, sometimes we don't have well defined objectives, because we don't communicate with the stakeholder and we don't know what is their exact expectations. Sometimes we don't detail. Sometimes we ignore the random variables in the model. Sometimes we just, rather than running multiple runs, we just do a single run and get the conclusion. And sometimes we use output statistics as true answer. And we use the wrong, in some scenarios we use wrong measures. So whatever the output statistics, that need to be discussed within the with the managers, based on their empirical knowledge, based on the expert opinion, based on the industry situation, based on the market scenario. The practical realities has to be built in, the empirical knowledge has to be built in, and the wisdom of the management, then the right decisions are taken. Sometime when we are dealing with big data and simulation model, it is, as far as the volume is concerned, the simulation model can use large data set to better define statistical distribution, and so more reliable inputs are more reliable if the volume is large for the simulation model. And simulation model focus more on relationship and less on causality, so it can be an appropriate to deal with the high complexity and with large amount of computation presented by big data. So simulation can be easily applied to big data. In summary, let me reiterate before I wrap up the session. Simulation models allow decision maker to compare alternative scenarios and control variables in ideal experimental conditions without altering the physical reality. So once you don't deal with the real system, you deal with the simulator system and run different alternative scenarios and keep what variables has to be kept constant and what are the input and output variable. Under experimental conditions, you save cost. If you have a simple model, then Microsoft Excel, I just showed you 2 examples. Microsoft Excel can be used. When models are complex and the complex business situation need to be analyzed, the methodology remains the same, but specialized simulation software can be utilized. The model validation, verification, and appropriate statistical analysis of output generated by such model is useful and shall be used for decision making. Thank you very much. I hope you got some inkling of simulation modeling and how and when simulation models are used in business decision making and running checks on or deciding between different alternatives and policy decisions. Thank you very much.